Hi, my name is Lindsey Scott.
My name is Jonathan Lacorazza.
And my name is Jacqueline, Noorollah, and our topic is the history of calculus based on Leibniz and Newton. Our topic is the history of calculus based on Newton and Leibniz. They both contributed to the field of calculus in different ways. Leibniz reported his findings first, but Newton wasn't far behind. However, both inventors claimed that they stole each other's work. Leibniz and Newton controversy continued until the end of their lives. Background of Isaac Newton. Newton was born on December 25, 1642. His mother placed him with his grandmother so he could remarry a wealthy man. His mother came back when her husband died and took him out of school to be a farmer. He failed and went back to school. Newton graduated from Cambridge University, and it was closed for 2 years due to the plague. During this time, Newton conceived the methods of fluxions.
This is Isaac Newton's definition of calculus. The method of fluxions in an infinite series with its application to the geometry of curved lines can be compared to a modern-day calculus textbook. It lists ways of finding both curvature and quadrature. Curvature is extrema, max and mins, and quadrature is area under a curve. Newton's work is heavily rooted in geometry, and in his work Newton writes a proof. The proof is derived from the following assumptions. It's derived based on the graph of a particle from the velocity equation. And so, as we can see on the next slide, Newton states x dot and y dot are the indefinitely little accessions of the flowing quantities x and y, by which those quantities are increased through the several indefinitely small intervals of time. X and y after any indefinitely small interval of time becomes x plus x dot o and y plus y dot o. So what is the change of x and y equal to? Well, the change in x is equal to x plus x dot o, and y goes to y plus y dot o. If we consider the graph of a particle going along a curve at some position x comma y, this new position is x plus some quantity, y plus some quantity. So Newton says that this quantity is x dot o, and this quantity is y dot o. And that comes from velocity in the x direction is equal to the change in x divided by the change in time. And so we get the change of x is equal to the velocity of x times the change in time. And so change of x, according to Newton, velocity of x is x dot, and change in time is o. And so it is the same idea with y. Change in y is equal to y dot o. So now we know what the quantities are. So we can, at some point x comma y, or the initial position of the particle, it goes to x plus x dot o comma y plus y dot o, the new position of the particle. So now if we consider a practice problem, let's consider problem f of x is equal to 1/2 of x squared, and let's see how Newton would prove his method of fluxions. He would first substitute in for y plus y dot o. Y plus y dot o is equal to, now we substitute in for x plus x dot o, quantity squared. So y plus y dot o is equal to 1/2 of x squared plus 2x x dot o plus x dot squared o squared, all coming from a double distribution of x plus x dot o. So now we can distribute our 1/2. Y plus y dot o is equal to 1/2 of x squared plus x dot o plus x dot squared o squared. So now we know what y is from the original equation. Y is equal to 1/2 x squared, so we can substitute 1/2 x squared in for y. 1/2 x squared plus y dot o is equal to 1/2 x squared plus x dot o plus x squared o squared. And so we can cross off 1/2 x squared on both sides of the equation. So now let's bring down everything that we have. Y dot o is equal to x dot o plus x dot squared o squared. Now let's divide by o. Since o is some non-zero number, we can divide by this number. So we have y dot o divided by o is equal to x dot o plus x dot squared o squared, all divided by o. So when we simplify, we get y dot is equal to x dot plus x dot squared o. So since we're assuming that o is some non-zero number, Newton also states that we can ignore what's being multiplied by this number since it's an indefinitely small amount. So we get y dot is equal to x dot.
Background of Leibniz. Leibniz was the son of a professor who studied philosophy. He died when he was 6 years old and was raised by his mother. At age 14, Leibniz entered the University of Leipzig. He graduated with a bachelor's degree and wrote his thesis to principal individuals.
So the fluxional equation we just found to the function 1/2 x squared is equal to y dot is equal to x dot. Alright, so the first issue that Newton saw was that we divided by some non-zero and so that's okay to do, but then our second assumption or second problem is that we ignore that term being multiplied by that non-zero number. So when we cross off our O's, O is still technically an amount, and then it's not a non-zero number, meaning that we have some number left behind when we're multiplying by a quantity that's not zero. So if we were to assume that it was zero, we can't divide by zero, so we can't do that division, but we could ignore our term that's being multiplied by zero. So Newton furthered this discussion in what he called the doctrine of ultimate ratios, in which he came up with the idea of a limit, which would be called a limit much later on. So this is Newton's proof of how he would find a fluxion.
So this is Leibniz's definition of calc. So he did not use limits. Instead, he used differential equations. The definition of it is an equation with a function one or more of its derivatives. An example of it is an equation with a function y and its derivative dy over dx. It is passing the infinite differences to an infinite small difference. The notation of it is dy over dx, derivative of x with respect of y. This is an example of Leibniz's calculus. We have a function of y equals x squared. So the derivative of x squared is 2x. From there, we have dy equals 2y times dx, and that is dy over dx equals 2x. So we have a graph of x squared, of delta x and delta y. So we have to try to find if it's infinite small difference. So we have y plus delta y equals x plus delta x squared. Now we have y plus delta y equals x plus delta x times x plus delta x, and we have to FOIL. The third step is delta y plus y equals 2x delta x plus delta x squared. And the final solution is dy equals 2x dx. So the differential of y equals 2x times the differential. So that is the solution. And that is dy equals 2x dx.
Our perspective of who invented calculus. Leibniz and Newton are two influential mathematicians who are given credit to the discovery of calculus. Newton is credited for discovering calculus, thus Leibniz should also be given the credit. Modern-day calculus uses Leibniz notation, not Newton's. Leibniz notation again is dy over dy and dx, and Newton's notation is x dot and y dot, which is no longer used. Leibniz also discovered the fundamental theorem of calculus, which gives the integral sign. Newton was not consistent with his notation, especially with that of integration, and Newton's results are as important as Leibniz's results. So Leibniz should also be given credit for the discovery of calculus.
I believe Newton discovered calculus. In 1669, Newton writes a treatise on fluxion but does not publish it. In 1675, Leibniz's notebook shows that he has the differential calculus worked out. In 1684, he publishes. In 1704, Newton finally publishes his fluxions. Many people would think Leibniz was the one that invented calculus based on the time, but it was Newton because he did the work before Leibniz but never published it. In 1711, John Peel publishes an article accusing Leibniz of plagiarism.
This is our perspective continuum, and this is my perspective. The Treaty of Fluxion in 1669 was written by Isaac Newton, but his work was not published. However, Leibniz's work that he did in 1675 showed differential calculus. Years passed, and in 1704, Isaac Newton published his functions. Newton published his book after Leibniz published his work first. Isaac Newton had more mathematicians add more ideas to calculus. Furthermore, John Cahill published an article accusing Leibniz of plagiarism in 1711, years 11 later. In response, Royal Society made a report that they are in Isaac Newton's favor. I believe Isaac Newton invented calculus because Leibniz was accused by plagiarism.
Alright, so this is our conclusion. Leibniz and Newton both made influential discoveries in the field of calculus. The slope of a tangent line is part of what method of function states define. It also includes finding extrema, max and mins, in area under a curve. Leibniz's discoveries include differential equations and also paved the road for integrals. Leibniz's notation of the integral sign dy and dx is still used to this day. Both Leibniz and Newton made influential discoveries in the field of calculus.